We're now doing one complete example of a Frobenius series solution to a differential equation. Here's the equation. X squared y double prime plus xy prime plus this times y. We already in a previous recording characterized our solutions. And we said this was a case 2 case. Well, first, 0 is a regular singular point, so we needed Frobenius series, not power series. But it was a case 2 case where we couldn't tell ahead of time if we would get 1 or 2 linearly independent Frobenius series solutions. So we have to go through the whole thing to find out. And that's the only way I know to find out. If it's a case 2, you just have to try. So the next step is to substitute in Frobenius series and its derivatives for y, y prime, and y double prime into this equation. You do that, you get this. This line here is just a direct result of substituting these y's and y primes into this equation. Then we could distribute the x's. We can take an x to the r out of each term and put in what's up in front. So here, this exponent's going to be n, just n, because we took the r out, and we added 2. So that's just an x to the n. Here, we take the r out, add 1, so that's another just n there. Here, we'll split this up. So we get n plus 2. And the other one will just be n. Bring in the 1/4. So that's what we did there, which means what's in brackets equals 0. That's shown here. And we can combine some of these terms. We have 3 terms that all start with n equals 0 and the power is x to the n. So we can combine all 3 of those terms. We'll do that right now. This algebraically simplifies, so this is what we can have to work with going to the next step. And well, before I get there, let's look at what powers they start with. This sum starts at x to the 0. This sum starts at x squared. So we want to pull out the first 2 terms of this sum, which will be C0 r squared minus a 4th, x to the 0, and for n equals 1, C sub 1, r plus 1 squared minus a 4th, x to the 1. And here's those 2 terms pulled out. Then we start, since we pulled them out, we'll start this sum now at n equals 2. And this is the result of all that. Then we adjust indices like we did with the power series. Turn our n's into k's. I'm not going to go through that. Need to get good at that, though. You can't just gloss over it. It's just, I don't need to do it a million times in these recordings. So at this point, we can apply the identity property to find all the recursive relationships. We already had the indicial roots, and they would crop up again from here. We already knew the indicial roots. So let's go through for the larger indicial root, which was 1/4. What happens to this term? When we apply the identity property, we already knew this term was going to be 0. This has to be 0. Every coefficient in front of every power of x has to be 0. So here's the x to the 0 term, here's x to the 1, and here's x squared and up. So this has to be 0, C1, and this has to be 0. If R was, I think I was wrong. The initial roots are plus or minus a half, not a fourth. So the larger initial root is a half. So let's put that into here. Get 3/2 squared, which minus a fourth, I just get 2. I get 2 times C1 equals 0, which forces C1 to be 0. C0 has to be non-zero, and we'll just set it to 1. So C1 is 0, C0 is 1. That was forced on us. Then we use this for the recursive form for the rest. Simplifies a little bit algebraically, I guess. This has to be 0. You put it in the recursive form, you get this. Simplifies a little bit to this. That applies for every k 2 and up. You know that from this sum. So we've got C0 and C1, and this will get us to C sub 2. So then we go through and crank through those. Here's the relationship. We start doing the arithmetic. And I get a bunch of numbers. Turns out all the odd ones are zeros. So what I get, put this together, I get a powered series, partly. You know, C0 equals 1, and C sub 1 is 0, then C sub 2 is 1 over 3 factorial, etc. I get what's in parentheses. But don't forget, the whole solution is that part also times x to the initial root. In this case, the larger initial root, which was a half. So here's that solution. Now, if you're clever and know what a sine series, what series a sine takes on, this is the Taylor series for a sine, or the power series. If I factor out let's see, factor in an x, anyway, I can rewrite it, pull out a power of x like this, and what's left in parentheses here is the sine of x. I would not require you to do this. If you took the course from me, I would not require you to do that on an exam or even for homework. But here we have one of the two particular solutions. It was based on the larger initial root. So now what do we do? Since it was a case 2, where a second solution might be possible, we have to try. But we do it using the smaller initial root, which was minus a half. So this is a half squared minus a fourth, which is 0, no matter what C1 is. And this is that case, that subtle case I was talking about. It makes C1 look arbitrary because it could be anything, and the identity property is still withheld or upheld. So we're going to set it to 0. And then we have the what the remaining recursive relationship is for this smaller initial root. And that we get this relationship for k equals 2 and up. But now C0 equals 1 and C1 equals 0 because we set it to 0 because it looked arbitrary. And I'll just tell you, if we treated it as arbitrary and did the 1, 0, 0, 1 trick, we'd get 2 solutions out of this, but one of them would match what we already found with the larger initial root. So it's not linearly independent of it. So we would have just created extra work for ourselves and not found any new linearly independent roots. We only get 2 at most. So continue with that recursive relationship. I'm not going to go through all this. We get more coefficients. Here's what you would get if you plug it in. And here again, we can recognize the cosine as a series. So here's the second particular solution. We now have two particular solutions. Again, don't forget this extra x to the r factor in front of things. That's one of the common sloppy errors that students make. And since we have two linearly independent particular solutions, we can find the general solution as a linear combination of them. And in this case, it can come in closed form because those sums were bounded to sine and cosine of x. And that's the whole thing. That's all power series and Frobenius series.